Whenever you've got a circuit diagram, you go from the negative terminal with one color until you reach a point where there is a resistor. Remember that the ammeters don't use any energy, so you can just go straight through them. Choose another color, go through the ammeter on the main branch until you hit a resistor. Choose another color, go from the resistor until you hit a resistor. You're then going to have over here, you could put another color there, but we'll call it black for today. And what are they saying to me? If the battery voltage is 18 volts, what is the voltage of each cell? Long stick, short stick, long stick, short stick, long stick, short stick. So that's 3 cells. Take 18, divide it by 3, and you land up with 6 volts each. Calculate the readings on V1, V2, A2. So it's all of the meters that are in this diagram. Let's try and make some sense out of it. It appears that we have got an external voltage of 18 volts. They don't say anything about internal resistance, so let's not worry about that for now. If I take a look at the place where I probably have the most information, it's going to be over here at the 4 ohm resistor. The reason for that is because I know it's a 4 ohm resistor. I also know the current on the 4 ohm resistor because the whole way on the main branch is going to be 1,5 amps. So I'm actually able to do a calculation over there, and I'm able to say the potential difference on voltmeter number 1 is going to be, remember, we've got resistance is equal to potential difference over current, and the potential difference is the resistance, 4 ohms, times by the current, and that is going to be equal to 1,5, and I land up with 6 volts. Now, with that 6 volts, I'm able to say, all right, if I was taking my story where I've left home, I'm having some dinner, and then I'm going to split up for the movies, I've spent 6 of my volts, of my 18 volts, to be able to have dinner. For the movies, in other words, the parallel network, I'm going to need to use up a further 12 volts. And that's for the whole parallel network. So between pink and orange, I have landed up with 12 volts. And therefore, I can easily say that voltmeter number 2 over here is also 12 volts. And then I know some information about downstairs as well. I know that the whole bottom branch is also 12 volts, but I can't split it into voltmeter 3 yet. I have got 12 ohms, I have got 12 volts, so I'm able to work out the current on this top branch. So let's go with I is equal to V divided by R. Potential difference in that particular resistor is 12, resistance in that resistor is 12, and I land up with 1 amp. I know that there was 1,5 amps on the main branch. It's split, 1 amp goes to the top branch. That means that I can work out that ammeter number 3 is 0,5 amps. Now I'm able to work out voltmeter number 3. Why? I've got an ammeter and a resistor, so I can say V is equal to I times R. The current is 0,5 and the resistance is 16, and I land up with 8 volts on voltmeter number 3. This question's actually got a whole lot of information in it. It's an electric heater. They give you a power value. They give you a potential difference. If the heater is operating at the design power, calculate the current. Well, we have an equation that links power is equal to potential difference times current. So if I'm trying to find the current is going to be equal to the power divided by the potential difference. So that's going to be 60 divided by 12, and I land up with 5 amps. A second heater is also designed to operate with a 12 volt supply, is constructed using an element with half the resistance. It asks then, explain quantitatively the effect of this change on the resistance and the power of the heater. So if I'm going to land up halving the resistance in this particular thing, I am going to say the resistance is going to be equal to V squared divided by the power. My potential difference hasn't changed at all. My power is still the same, and therefore I can work out a resistance of 2,4 ohms. Half of that resistance, if I were to take a look at it, So if I halve that resistance, what would happen to the power? It's going to land up being a relationship where there is an inverse proportionality. So if I look at the proportionality here, I land up with resistance being inversely proportional to power. So if I were to halve the resistance, I would land up having to double the power. Taking a look at this particular circuit, battery has an EMF of 12 volts and an internal resistance is stipulated here. It is connected in a circuit with 3 resistors, each having a resistance of 10 ohms. One of those resistors is in series, 2 of them are in parallel. And we get told a current flowing through the battery. If the current is flowing through the battery, that means that it is the main branch current. So if we're going to take some colors and just mark that circuit for a second, we're going to go from the one terminal split, from the other terminal, and I'm going to go all the way through this resistor, because this resistor is actually part of the battery. It's the internal resistance, until I get to the first external resistor, and then from that external resistor I'm going to go until I hit the parallel network again. First thing they ask me to do is to calculate the potential difference between point A and B in the circuit. So that means that I have got a series current. I'm going to just pretend that I do not know what how that current is splitting. Well, it's going to have to split evenly, and they want to have a potential difference. So it's as if I had a voltmeter connected over there, and I'm able to say V is equal to I times R. But before I can work out what the resistance is, I'm going to have to say 1 over R parallel is equal to 1 over 10 plus 1 over 10, which is equal to 2 over 10. And R parallel, don't forget you have to invert it, is going to be 10 over 2, which is equal to 5 ohms. I then use the equivalent resistance of the whole network. So I'm going to put a circle around that and just write 5 ohms in there, because that has been reduced to, in essence, a single 5 ohm resistor in series. And when I've reduced it to a single resistor or an equivalent resistance, I can then use my series current which I've been given. And in this case it is 0,5. And that means that I'm going to have 2,5 volts between A and B. The next thing they ask us is, what is the internal resistance of the battery? Well, we can work out what the external resistance of the whole circuit is, and from that we'll be able to work out the potential difference that is going to that external circuit. So the first thing I'm going to do is I'm going to say I've got 5 ohms. My R total, or my R external rather, is equal to the 5 ohms from the parallel network as well as the 10 ohms from the series circuit. So I land up with 15 ohms. I'm then able to say that the external voltage is equal to current, which we now in a series situation, 0,5 multiplied by resistance, the total external resistance, and I land up with 7,5 volts. That tells me that the internal potential difference, which is our lost volts, same thing, is going to be equal to 12 minus 7,5, and that turns out to be 5,5 volts. I'm then able to look at the internal resistance, because internal resistance is equal to the lost volts divided by the series current. And therefore it's going to be 5,5 divided by 0,5, and I land up with 11 ohms of internal resistance. What is the total energy supplied by the battery in 2 seconds? Not terribly tricky. I'm going to, work done is energy transferred, so its work done is VIT. it's to the battery, the total energy supplied. So it's not internal, it's not external, it's total. So I use the 12, the EMF. The current going through is 0,5, and I was told a time of 2 seconds, and I land up with 12 joules. And what fraction of the energy supplied by the battery is dissipated within the battery? In other words, how much energy gets used by this internal resistance? And so for that, I can use a number of different equations, but I do know that I have the current, I have the potential difference, and I have the resistance, but I'm going to choose to use W is equal to I squared RT. The current is 0,5 squared. The resistance is 11 ohms, and the time is 2 seconds. I'm using the same time because I'm seeing how much did I lose in the exact same time, and I get 5,5 joules. So then what percentage has been lost in this situation? And I land up with saying, well, 5,5 out of 12 joules has been lost to the internal resistance, or inside the battery. Times that by 100, and I land up with 45,83% was dissipated within the battery.